Okay, so we said that with the distributional semantics, the important thing was the find the distribution of all the words that appear together. Okay, for example, take this word banking and find all the words in our corpora that appears with banking, and try to find a formalism that explains this in terms of probabilities. What is the probability of seeing these two words together? If we can do this, if we can explain this probability, then we are in a position to talk about the language modeling, and we are in a position to talk about the words. Okay, that's what we said last time. We said that suppose each word has a vector like this, 100-dimensional or 200-dimensional or 300-dimensional, doesn't matter. Such word representations would be generated out of this idea, okay, from the distributional semantics, and we developed our formulations accordingly last time. And we said that word2vec is one of the examples of doing such a thing, giving a corpora unlabeled corpora by analyzing how the words appear together. It assigns vectors to each word, and it does that using this probability given WT given into what is the probability of I am seeing banking, or what is the probability of seeing crisis, etc. That's what we said. And to calculate this probability, we said that we said that each word will have a vector. Okay, each word will have a vector. Using those vectors, we are going to calculate this probability. Let me show you the probability first, and it is this one. Okay, so we call this softmax last time. I'm just trying to review what we have seen last time. Okay, we said that given the center word, what is the given the center word, what is the probability of seeing this context word? Okay, we said that if UO is the center words vector, and VC is the center words vector, UO is the context words vector. If you multiply these two vectors, these are just regular vectors, 100-dimensional vectors, real valued vectors, we will get a number, and we divide this number with this summation. Okay, could somebody tell me why we use exponential here? Could somebody tell me why we are using exponential in the upper part? Somebody explain to me why we are using exponential in the upper part. Okay, tell me the range of this multiplication. What could be the result of this multiplication? It says scalar, right? What would be the smallest value and the largest value out of this multiplication? Okay, from the beginning, let's start. Ahmet Semih Özmekik. Ahmet, tell me, What is the smallest number out of this multiplication? Ahmet, Semih?
I think we should, like, we are doing this to make probabilities between 0 and 1.
Yeah. Yeah, that's exactly right. So then in that case, maybe you can explain why are we taking the... So tell me, what is the multiplication of these two? Okay, this is a 100-dimensional vector. Okay, UO is a 100-dimensional vector. UO is a 100-dimensional vector. Okay, and if I multiply this, okay, let me make this a transpose version because it one takes, okay, this is 100-dimensional and VC is 100-dimensional too. If I multiply these two, what would be the smallest number and the largest number out of this? Because this is a dot product, it's a scalar, okay? What is the smallest number and the largest number? Okay, Ahmet, Semih, I am asking you.
Okay, I'm thinking. So, I think the smallest number will be 0.
Okay, let's look at one of the examples of these vectors. Okay, here's an example of a vector. If I multiply this vector with a similar number, with a similar vector, what would be the smallest? There are minuses in it, right? It cannot be 0.
Yes.
And some of, I mean, by coincidence, some of these could be, what?
-1.
No, some of them could be as large as 1,000, -1,000. I mean, these vectors are just vectors. I mean, they don't have any features. So this multiplication could change from minus infinity to plus infinity, because those are just vector numbers, are arbitrary numbers. So the result of this multiplication is from minus infinity to the plus infinity. So maybe you can tell me why we are taking the exponential of that number. Remember, how does the exponential work? This is exponential, right? Okay, exponential e to the x is, when x is minus infinity, it is 0. When x is 0, it is 1. When x is 1, it is e, right? So why are we taking the exponential of this multiplication?
To fit this infinity range into 0 and I think
0 and infinity, right?
Yeah.
So this will make everything positive. And the same thing is here too. But in this case, UO is going to be one of them, right? So out of all these W's, one of them will be O. In that case, this equation is going to be between 0 and 1.0. So it's a probability, right? If two vectors are similar to each other, this P is going to be large as 1.0. If they are not similar, it is going to be as small as 0. So what you said at the beginning is correct. Okay, what you said at the beginning is correct. So we are doing this just to fit everything between 0 and 1.0. So whatever you give, it cannot be smaller than 0. Whatever you take out of this, it cannot be larger than 1.6. What we expect out of a probability. That's what we said. And if we have a a loss function like this, what does this say? It says that okay, one thing here. P is like this. P is defined like that. P is defined like that. Why are we taking the minus log of this P when we calculate the objective function? Can anybody tell me what objective function is? Can anybody tell me what objective function is? Okay. Ahmet Melih Yanalak. Ahmet Melih, can you tell me what an objective function is? Ahmet, are you there? He is not here, so I am removing him from the meeting. Okay. Ali Haydar, can you tell me what an object function is? Objective function is? Ali Haydar, are you here? Okay, he is not. So he is gone. Aras, can you tell me what objective function is?
To doing something minimized or optimal. Different things.
Okay, so what is the thing that we are trying to optimize here? That's exactly right, yeah.
Average of MLA.
Average of what?
The words probability maybe.
Yeah, this the probabilities of these words, right? I mean, if you have a large corpora, right? And if we make this probability large, that is, given this banking, what is the probability of crisis thing, right? Make this as large as possible. So just to minimize this, we put a minus in front, right? So minus is just be like P is larger, as large as 1.0 for each one. But to make this a minimization problem, we put a minus in front. How about the log? Why are we taking log?
Underflow.
Just say it again.
To prevent underflow.
Mustafa, that's a good answer, but I mean, in this case, we are not multiplying anything, okay? We are just adding stuff. With the addition of the probabilities, we don't have an underflow problem. We take the log of this probability because we like to dampen the effects of sudden peaks in the addition. Okay? Sudden peaks in the addition. Okay, that's the reason. So we call this negative log likelihood function, and usually we do this that way. Okay, so we add. Okay, can somebody tell me what this M is? I am asking exactly the same question that I asked last time. Can somebody tell me what M is?
It is window size.
It is the window size. Yeah, for the center word, okay. What window should I look at it? Like 5 words before, 5 words after, etc. Right? That's what we should do, right? Okay. So
can you hear me?
Yes.
Okay, my microphone wasn't working before. If we then take the logarithm of it, would we have to multiply them in the cost function?
If we take the logarithms of it,
if we didn't take the logarithm of it, wouldn't we have to
No,
multiply?
actually, no. Well, I mean, we are saying that, I mean, this is not, we are saying, this is what we are doing, okay? Let's say we took this as a center word, okay? If I take this center word as a center word, this is our summation from -2 to +2, okay? From -2 to +2, I calculate, okay, this is -2 is here, -1 here, -2, -1, 0, +1, and +2. So I get all of them, multiplication, all of the probabilities, and I add them together, okay? And I make this my center word, then this becomes -2 and -1. I keep adding them, okay? I keep adding them in this case.
Okay. Also, you said the word vector doesn't have a feature, but doesn't every element has to be probability 2 in a vector? Or
Say that again. I did not understand what you asked. Sorry.
you said the word vector doesn't have a feature, but does the elements of word vector have to be between 0 and 1?
No. It doesn't have to be. No, we don't force them to. We don't force them to. Okay.
Okay.
I think you were mentioning about this, maybe. Huh? Are you mentioning about this? This is the likelihood. Likelihood of seeing everything. Yeah. This was multiplication. Then we took the logs of it, and it became like that. Yeah. Okay. Yeah. Well, yeah. Sure. I mean, in that case, this formula is for adding stuff. Okay. You take the logs and add them, but originally our likelihood of seeing all of them together was this. Yes, that's true. Okay. But we take the log here. Log is going to be a nice function. Okay. A negative log likelihood. It will dampen the peaks, some of the peaks. Okay. So this is, given the corpora, this is what we are trying to optimize. Find parameters. What are the parameters? Parameters are our vectors of the center words and the context words. Okay. Find parameters in a way that this objective function is minimized, because I am using the negative log likelihood. Okay. That's what we said last time. And probabilities of, given the context word, what is the, given the center word, what is the probability of context word? Is done using the softmax. Okay. This is word-to-vec prediction function. That's what we said, and we said that we are going to do this using gradient descent. We are going to start, let's say, in this function. Okay, objective function, we are going to assign random values to these parameters, all of them, and we are going to calculate this objective function, and we are going to say that, okay, let's change these parameters in a way that it decreases our objective function value, and we are trying to make it as small as possible. Okay, so that's called the gradient descent. So how do we find the gradient direction? Of course, gradient descent, we take the derivative with respect to okay, all those parameters. So it's going to be one huge derivative, because there are if I have 40,000 words, and each word has 100 dimensional vectors, it is going to be 4 million numbers, okay, 4 million parameters. So I will take the derivative of that objective function with respect to 4 million parameters. Okay, so I'm not going to do it once. I am going to do it many times. So if I do it this way, if I do it in a straightforward way, that's not going to be easy. That's why we have found some ways of achieving this. Okay, I guess last time I was assuming that my word vectors are like 200 dimensional. So does anybody remember this 2? Does anybody remember that 2? What is 2? I have written here 2 times 200 times 40,000. What is 2? Where does 2 come from? 2dv. V is the vocabulary size, d is the vector size. What is 2? Okay, Aynur, do you know what 2 is? Take a guess. What is 2?
2 for 2 dimension of words. For example, for one words, we have another words together as a probability of that.
For each word, yeah, that's true. For each word we have 2 vectors. One is for the center vector, the other one is the context vector. So for some reason they preferred it this way. So this optimization will assign 2 vectors for each word to make the optimization a little bit easier. That's what they say. Okay, so and I think we looked at this a little bit. If I like to take that j function dj, which is our objective function with respect to the parameters, then I am finding the gradient direction. I am saying that move towards this gradient direction, and chain rule says that if this parameter depends on some other stuff, then you need to take the derivative again, multiply them. Okay, so computing all the gradients is not easy. Okay, computing all the gradients is not easy, so we are going to find something else in a few minutes. So if we are in a one-dimensional world, okay, and if our function is like this, finding the minimum using the gradient descent is guaranteed, but in that case we are not in a single dimensional world, and our objective function is not as nice as this. This is a convex objective function, but in our world our objective functions are like this. Okay, we don't know the minimum of it, we don't know the maximum of it. Okay, we don't know, we simply don't know the minimum and maximum of it. And if we are lucky, let me try to draw this in a better way. Okay, so single dimensional problem. Okay, if we are lucky, if I started here, it will drop down to the global minimum. But if we are not lucky, if we started here, green, it will drop down to here. Okay, like that. Okay, so what we are here trying to do is finding the global minimum, of course, but gradient descent is not going to give us the global minimum all the time. In fact, almost all the time it will never give us the global minimum. It's going to give us some kind of a local minimum, but it's not going to be a global minimum. But we don't have anything better than this, because we are living in a world of what was our size again? 2 times 200 times 40,000. Okay, millions of parameters, millions of dimensions. Okay, that millions of dimensions is somewhat problematic. It is not easy to work in those kind of dimensions, but this is the best we can do, and there are many cases that people show that this works. Okay, so gradient descent is something that we are going to do. We are going to do this. We will start with the initial parameters. We will take the objective functions derivative with respect to those parameters, and that parameter will that derivative will give us the direction, and we will move towards that direction with a step size of alpha. Alpha is the step size. For example, in this case, alpha is going to give us large step sizes. Okay, question for you. Why are the step sizes are, in this case, large, but now it is small? Why are we moving faster here, but moving smaller there? This is what we are doing. This is what we are doing. Anybody?
The gradient is steeper there, so
the gradient is very steep here. Okay. If it is steep, then this number is going to be large. Although alpha is the same, I will move a lot faster with respect to this, relative to this old parameters. When the gradient is flat, okay, it will not make me move. So at the beginning it is fast, but then it becomes smaller and slower and slower. That's one of the problems with the gradient descent, actually. If you don't have a nice curvature, nice convex structure like that, sometimes your progress is going to be slow. Yes, Selman, you have a question?
I want to
So
add
Selman,
something.
it worked. I kicked you out and you started talking. Yeah, so I'm going to do it more often.
When did you kick me?
I didn't kick you out.
Today?
I thought I kicked you out. You didn't answer me. Okay, good. So imagine I kick you out. You would talk even more. Sorry. Okay, so that was a joke. Okay, you ask your question.
Did you kick me last week?
I don't know. I thought I kicked you out a few minutes ago. Who did I kick?
It was Melih, I think.
Okay. Did they come back?
I don't know.
Okay. Tell them come
But-
back. Okay, ask
you
your
could
question.
Kick me because my mic wasn't working. It's actually isn't a question because I read somewhere the more parameters we have, the local minima is generally more close to the global minima because the probability of having a local minima on every dimension gets really low.
Yeah. Yeah, well, that's what the deep learning people say, is that, okay, the number of parameters being large sometimes advantages, but we definitely know that local minima is going to be a problem. Sometimes our optimization doesn't go anywhere. Okay, that's a good point too. Okay, but we have more problems than this. I mean, this convexity thing, and we're gonna see. The problem is we have millions of parameters to optimize, millions of dimensions to move on, and if I take the derivative of those this objective function with respect to those millions of parameters, this calculation is going to be so expensive. Every time I like to take a step like that, okay, by the way, I'm taking millions of steps, millions of updates, it's going to be so expensive, so I am not going to do that. Instead, we will do this. Okay, this objective function is a function of all windows in the corpus. Okay, all windows means that if I have a billion words in my corpora, okay, so this objective function is going to be calculated at billion different positions. So that means that this J, find my J, this J is going to be calculated from 1 to 1 billion. Okay, that's going to be so expensive. Every time I will calculate this, then after the calculation I am going to take this derivative, which is going to be again expensive. So what are we gonna do is I will use this stochastic gradient descent. What does that mean? It says that don't calculate this j theta on all the word positions. Okay. So what should I do? Maybe just take 10 words, 10 random words, calculate this j theta, and calculate this gradient on those 10 words, and update your lambdas accordingly, update your thetas accordingly, and then come back and take another 10 words. Okay, so repeatedly sample windows and update after each one. That's what we are going to do. So we don't do that calculation very often, and we do this using this stochastic gradient descent. It is gradient descent, but it is stochastic. Why is it stochastic? It is stochastic because we take, let's say, 10 random words, 10 random windows, and calculate j theta on that only. Okay, and continue until you have used all the word positions. There is no running away from calculating all of your stuff on those 1 billion positions, but we don't take our steps after the evaluation of 1 billion positions. We take steps after evaluation at 10 or 16 or 32 positions. Those 32 positions are called batch sizes. When I say 10 positions, okay, it is batch size of 10. When I say 32 positions, it is batch size of 32. Usually our batch sizes are powers of 2 to the power n, 2, 4, 8, 16, 32, etc. It goes like that because that's a nicely addressable batch size, and usually we fit those batch sizes on our GPU, and on the GPU calculating stuff is easy then. Okay, so that's the gradient descent, and we are going to look at them more carefully in a few more minutes. Okay, any questions so far? Any questions so far? Okay, if there are no questions, let's move on. This is approximately how we are calculating those thetas. Okay, those thetas. I think last time we stopped a little bit earlier than that, but basically our basic formulation is this. Get your corpora and try to make this. Get your corpora and try to, come on. Get your corpora and try to make this multiplication as large as possible, but we take the negative log likelihood of it because of its nice features, and then we ended up optimizing this objective function. Okay, good. If there are no questions, then I will continue with the next slide set. Again, I took this from Manning. There is something funny going on. I don't know. I mean, let me start this program again.
Were we going to talk about negative sampling?
Negative sampling, I think I talked about it a little bit last time. But basically it is this. Remember that softmax function, exponential of UO times VW over something. Do I have it in here? Okay, so this one. Even if you are using batch stochastic descent, okay, stochastic gradient descent with batch sizes, this formula calculation of this probability means that you have to multiply the center word with the context word first, but then for all the words in your dictionary you have to calculate the denominator. So the denominator is going to be something expensive because we are talking about 40,000 words in here. So the negative sampling says that, okay, don't calculate all this, just pick random, let's say 30, 40, 50 random words and calculate this on those negative words, okay, and then make this division. So instead of running this against all the words in my dictionary, I am just running this against maybe 1% of all the words. Okay, so this will make it 100 times faster. Okay, maybe that's who asked that question? Selman, did you ask that question?
Yes.
Okay, parameters of word to vec. Maybe looking at these parameters is kind of make it more understandable for you. Word to vec parameters, when you are using it, it will tell you the meanings of it. Where are those parameters? Okay, no, not this one. Parameters. Okay, good. So when you are running word to vec, first it wants the sentences. Okay. In this case, what is this? Is this a Python implementation? I don't need it. Okay. Our sentences are corpus file, path to corpus file. Format you may use as argument instead of sentences. So instead of sentences, it's a file. Okay, we know it. Vector size we know, right? It is how large vectors do you want? 100 dimensional, 200 dimensional, 300 dimensional. Okay, it wants you to do that. Window is, again, remember that m, the number m here. Where is m? This one is window size. Okay, now we know that too. What else? Workers, usually these can be done in parallel. Why? Because this is just, remember this one? This is just addition of bunch of numbers, okay? So each iteration of this sigma can be done separately, okay? So if I assign a different thread for each iteration, then I am going to be fine, right? So that's the workers SG. Okay, again, remember, skipgram or continuous bag of words. One is given center word, calculate the probability of context word. The other one is given the context word, calculate the probability of syntax word. Okay, so skipgram or continuous bag of words. HS is hierarchical softmax. Again, hierarchical softmax is so expensive here. How many possible softmaxes do I have in here? 40,000, right? 40,000 softmaxes. Why? Because given the context word, given the center word, what are the probabilities of all the context words? Sometimes people don't use it directly. They use it this way. Let's say they say that, okay, let's say that, okay, when you calculate POC, how many center words are there? 40,000. They say that, okay, if I have 40,000 words, I am going to group them okay, 1000 by 1000, and there will be 40 groups, okay, 40 groups of words, and the first group will be W1 and the last group will be W40, okay. So in my corpora of 1 billion words, I am going to replace the words by their group number. So instead of calculating this on 40,000 words, okay, I am going to calculate this on 40 words only. When you do this on the 40 words, okay, it's going to give you an approximate probability assignment. After that, after doing that, I can divide each of my group into, let's say, what was my initial grouping, 1000 words, maybe 1000 words per group. Maybe I will divide this into 100 groups. Well, in that case, each group will have 10 words. The second level of probability calculation. So this is what the hierarchy is. Okay. If you want hierarchical softmax, then this is 1, otherwise 0. And if 0, instead of hierarchical, remember, negative sampling is something like that too. Okay. If you use 1, a hierarchical softmax will be used, and your softmax will be cheaper to explain, cheaper to calculate. If 0 and negative is non-zero, negative sampling will be used. Okay, so either a hierarchical softmax or a negative sampling. So negative sampling will be used in the negative, specifies how many noise words should be drawn. Usually between 5 and 20. Remember, what did I say? I said you look at 10 words or 50 words. I don't remember. So you, instead of you looking at the whole vocabulary, you are looking at 5 or 20. Okay. So what else? N as exponent is something that is used to calculate the probabilities when you use the negative sampling. Okay. What else? SIBO mean, continuous pair of words mean. If 0, use sum of the context word vectors. Use 1, use the mean, only applies to SIBO views. Okay, so remember we have 2 sets of vectors. At the end, which vector you would like to use? Either the sum of the context word or directly the context word itself. Alpha is the alpha that we see here. Alpha is this one. Alpha is the step size here, this one. How large it's going to be. And mean alpha is, I mean, you don't keep your alpha the constant, you keep changing it. Okay, so that's the mean alpha is start alpha from 0.1, but at the end is going to be 0.001. Okay, so it can drop down to minimum alpha. Okay, since we are doing this in a gradient descent, stochastic gradient descent way, loss of randomness is going to be happening. So if you like to provide a seed for this randomness, then you can do that. Max vocabulary size you don't know. I mean, okay, you give the corpora and corpora is counted, okay, and it determines the vocabulary size there. But if the vocabulary is too large, you can put a maximum here. Okay, maximum final vocabulary is something related. Okay, sample is threshold for configuring higher frequency for are randomly downsampled. So if you have words like and, or, one, two, I, me, etc., these are high frequency words, You don't want to use all the positions of these high frequency words. That's going to affect your optimization. So I can sample them. Okay. And it's optional. Okay. At the beginning, I need to assign some random numbers to the parameters, those thetas. Okay. This hash function will be used to assign those weights at the beginning. Epoch means that every time you go over all of your 1 billion words, that's then 1 epoch. And how many epochs do you want to do this? Okay, you can give it to that. Okay, I guess, oh, there are so many, so, okay, let me show you, okay, batch words. Okay, how many words in a batch in the gradient, stochastic gradient descent is given here. Okay, good. So many parameters, and most of them are good to understand what's going on with the word vec. Okay, some of them are about vector sizes, some of them are about like alpha, how we optimize stuff. So Selman, your question was your negative sampling sizes, and there are many other details of word vec. I think the best way to become familiar with them is to download this code and run it on your own corpora.
Yes, thank you, sir.
Okay, so let's go back to the slides. Okay, so once we calculate our vectors, we can use single value decomposition principal component analysis, or TSNE, to visualize them in 2 dimensions, and with the 2 dimensions meaningful stuff come back. Okay, but now I like to take one step back and try to do something that is more classical than word2vec. Okay, we will call it co-occurrence matrix. Okay, we will call it a co-occurrence matrix. In the co-occurrence matrix is this. Let me give you one example. Let's say my corpora is as simple as this, just 3 sentences, like 10 words in it, very, very small. Compared to 1 billion words, this is just a toy, even simpler than a toy example. Okay, so let's try to calculate the co-occurrence matrix. Co-occurrence matrix is this. How many times did I see I and learning together? How many times I see I and like together? Okay, so it's a 2-dimensional matrix. And if I calculate the co-occurrence matrix on this one, I get this. I see I and like 2 times together. Here is I like, right? I see I and enjoy just once. So it looks like my window size is very small, just 1 word, right? How many times I have seen NLP, like NLP, and dot NLP. So my window size is obviously 1, -1 to +1. Okay, -1 to +1. So that's the occurrence matrix. Some people say that, okay, this is good. This is good enough to be a vector representation of the words. Okay, NLP could be represented with this vector of size 1, 2, 3, 4, 5, 6, 7, 8. Why is it 8? Because there are 8 words in my vocabulary. My vocabulary size is 8. Okay, so 8-dimensional vectors for each word. Of course, since this is a toy example, my vector sizes are coming back very, very small. But if I am in a real corpora, my vector sizes will be 40,000 or 400,000. Okay, depending on the depending on the type of the corpora, the type of the sentences, or the language itself, Turkish or English. Okay, Turkish or English. So why don't we use to represent words? And it turns out that this works very well. This works very well. Okay, and it gives you idea about the meaning of the words. It gives you ideas about the syntactic relations between the word and etc. Okay.
Why we use punctuation like that in that matrix? We generally talk about the words.
Yeah, the punctuations are treated like words in this case, because I mean, in order to find syntactic features of words, I mean, in English, if you think about English, okay, usually the last words of sentences are nouns like that, right? So that dot is giving me idea about the part of speech tags of the words. In Turkish, usually the last word in a sentence is the verb, right? And the beginning of the sentences, like it starts with I, la, I, you, we, they, etc. Okay, so they are giving me lots of information. So treatment of the punctuation like the words is a good idea. I don't take out the punctuations from my corpora. I use them. Okay, so that's a good point. We have word2vec. What are the positives of this co-occurrence stuff? Co-occurrence invention is older than word2vec, and we are going to look at it. But there are some problems with it. What are the problems? It increases in size with vocabulary. My vocabulary is 40,000, then my vector is going to be 40,000 dimensional. Okay, loss of space. Okay, and nobody creates the word vectors just to create word vectors. Okay, you are going to use it somewhere. If you use your vectors, word vectors, using the co-occurrence vectors, okay, whoever is going to use it will have lots of problems with data sparsity problems, because most of the numbers here is going to be 0, and you have to deal with it. You have a 40,000 dimensional vector with many zeros on it. Okay, but okay, there are some good properties about co-occurrence vectors too, and we are going to see it in a few minutes. Okay, we are going to see it in a few minutes. So to solve these problems, what they do? Okay, most of the problems are about the high dimensionality of the vectors. To solve these problems, they did the dimensionality reduction. We don't like 40,000 dimensional vectors. I like to drop it down to 1,000 dimensions or 25 dimensions or something in between, similar to word2vec. So how am I going to do that? Let me take 10 minutes of break. After the break, we will continue with this dimensionality reduction. Okay, let's be here around 1439.
O şey benim fikrim var. Şey değil. Ona biz karşı. Olay yapılıyorsa şey yapacak. Alttan mı ya? Tamam. Yani o hani biz şey yapalım, öncelikle alana bir bakalım dedik, biz karşı. Ama işte ama bir zaman önce. Öncelikle alana kadar dedik mi? Şuradan olsun. Öyle mi? Olabilir ama başka şey değil. Böyle bir şey isteklerimiz oluyor diye düşünüyorum. Eğer siz istemediğiniz, yani almak istemediğiniz bir insan gelirse, almayın. Ama onun için aslında bir şey yok yani. Eğer böyle bir durumda sağlıklı ben de şey yok yani. Yani nasıl böyle bir ilgili olursa üç yüzde daha böyle. Yok ya çok fazla ki. Ben güvenlik neyse Profesörden yapmışlar. Profesörden yapmışlar. Gördün mü? Felsefe bölümü yapmışlar. Şeytanla başı çıkacak. Bir adam oluyor. Özellik bu. Eski inanı yok. Harbiden. Nasıl edilmiyor? Hocam bana nasıl edilmeyecekler ya? Şeytanlarda saçmalar var bunun gibi. Gel hocam, gel. Bir saniye, Kur'an ve sünnet rehberliğinde şeytanla mücadele edecek insan eğitimi üzerine çalışma yapmış olmak. Böyle bir şey var mı lan? Felsefe ve din bilimlerinde Kur'an ve sünnet rehberliğinde şeytanla mücadele edecek insan eğitimi üzerine çalışmalarda bulunuyor. Şu anda Karaman Üniversitesi'nde internet şu an Karaman Üniversitesi'nde böyle ilk dalga geçiyor. Karaman Üniversitesi, Karaman Üniversitesi şeytan eğitiminde yardımcı tutuldu. Ya kimi çağırmıyor? Hocam gelsinler burada var. Anlamış değil. Felsefe bölümü var. Ama felsefe din bilimleri yazıyor. Yani beraber farklı videolardan oluştuğu felsefe bölümleri o şeyler orada. Ben de çok iyi herhalde. Ama şey yok yani, şey yapmazsa artmış olabilirler. Almayız olabilirler. Bu kadar basit yani. Ya ama bu basit şey için açıklı değil bak. Şimdi şu ana kadar kırlanmıyorduk da sen bizim istediğimiz alanlar değil deyince kırlanmaya başladın. Mesela çok temiz. Yani tamam. Bu bir şey. Bu yoktu ya. Bak. Bizim istediğimiz ölçekli alanlar onlar yoktu bizde. Yöntemler olmuş. Yöntemler
iki tane doğru. 6 tane bulamayacağımız bir kanat değil mi ya? Oğuz'u da beraber vermişti. 2 tane daha dayanmışlar.
Ama Oğuz o yüzden böyle 6-0 işte. Ben de 2-0 yazınca Oğuz zannetmiş. Ulan asıl şeyden olay orada olmamışlar. Ben Oğuz'a 2-0 yazdım, o da bana 6-0 yazdı.
2-0 niye yazdın sen?
Yani iki kişi nasıl soktu Oğuz'a?
He,
Sen yazdım 2-0.
He.
O da bana 6-0.
Sen 6 olduğunu bilmiyordun. Sen kaç gol yediğini bilmiyorsun.
Ben bunu bilmiyorum.
Makine de 2-0.
Makine de olsa.
Okay. Let's continue. Dimensionality reduction usually is done with many areas of engineering and science. For that, we use singular value decomposition. It's a standard matrix decomposition technique. It says that given any matrix, it doesn't have to be square, okay, n by n matrix, I can decompose this matrix into 3 parts: U part, sigma part, and the V part, okay. This sigma part is a diagonal matrix. Diagonal means that only the diagonal elements are going to be non-zero. Okay, the rest of the matrix is going to be 0. U and V are orthonormal. That means that each column of U, since this is VT, okay, each column of V are orthogonal. If you multiply them, dot product, if you use dot product, inner product of them, it will produce 0. So what this singular value decomposition does is that, okay, let's say this is your co-occurrence matrix and it assigns a 40,000 dimensional vectors for each word. So this is a very large one. So it's a 40,000 by 40,000 matrix, right? It's a very large matrix. It says that I am going to, since this is a square one, it doesn't have to be square, but it is a square. I am going to make this a 40,000 by 40,000 matrix U, 40,000 by 40,000 sigma, and 40,000 by 40,000 V, okay? But single value decomposition says that, okay, I transformed your 40,000 dimensional space into another 40,000 dimensional space. But in this space, the important vectors are at the beginning, okay? So this is your first vector, second vector, third vector, etc. So you don't have to use all of the vector elements of 40,000. Using only the first 101 or 200 is good enough. Okay, so rest of them you may ignore and you will not lose much information. That depends on how many non-zero elements are in the diagonal, okay, and how far they are from 0. If they are close to 0, then you may ignore the corresponding vector, okay, corresponding dimensionality, sorry. So singular value decomposition by itself do not reduce the space size, but it rearranges your space. It transforms your space into a new space. In that space, you know which dimensions are important. First 100 is important, or first 200 is important. The rest you may ignore. That's what we are gonna do with the co-occurrence matrices. Okay, there is a very small Python code. Okay, import numpy as np. Okay, under the np there is a linear algebra section, and I have my words, an array. Okay, I have this np array. This is my co-occurrence matrix. Okay, this is my co-occurrence matrix. Inside my co-occurrence matrix, I put all of those numbers and I do singular value decomposition of the x, okay, which is this one, u, s, and wh. These are the U is the first matrix, and this is the diagonal matrix and the V matrix. Okay, and then this guy is doing this. It says that I is range of all the words. Words are here. Okay. For all the words, find the corresponding vector, two-dimensional vector. Take the UI. UI is the vector that corresponds to the word I. But take the first element of it and the second element of it. That's going to be X and Y positions in a graph, and the label for that one is going to be words I. So if I do this, I get two-dimensional visualization of those 9-dimensional or 8-dimensional space. Okay, so deep and NLP is close, like and I are far away, but you don't expect this to be very meaningful. Why? Because our corpora is very, very small. Okay, but basically that's what we do. So all you need to do is just get this the co-occurrence matrix, run the singular value decomposition, and pick the important dimensions, and use those dimensions to represent your vectors. Okay, that's what we said. Okay, with this approach there are some problems, as we said before. Okay, sometimes frequently occurring words such as the, he, has, etc. Okay, they messes up all the calculations. So some hacks, some solutions tell you that ignore them all. That's going to fix some problems. Okay, if you ignore them. Okay, and sometimes they say that don't use the word counts as they are, put them in a ramped function and etc. That will make all the calculations right. But at the end, when you do this, this is what you're gonna do. This is what you're gonna get if you use the two-dimensional visualization of your words. As you see, I find some nice syntactic similarities. Stolen, steal, stole, stealing. So all the words related to stealing are put together. Okay, these are all take. So again, this is 100% unsupervised. By looking at the corpora only, the words only, in a large word data set, I could say that take and taken, okay, stole and stolen and steal and stealing, they are close to each other. Okay, so it learns these syntactic relations in an unsupervised way. Okay. Abi dersten çıkınca arayayım, olur mu? Vallahi ben de bilmiyorum ki ya. Olur inşallah, sağ olasın. Okay, so this is what you get when you do the word co-occurrences. The relations that are reflected here are syntactic, but semantic relations are taken too. As you see, teacher, doctor, bride, priest. Okay. Drive, clean, swim, learn, teach. So these are kind of occupations of people, right? So these are occupations of the people. They are all different occupation names, and these are the things that people do. Okay, swimmer swim. Okay, janitor clean, driver drive, etc. So it knows the semantic relations. It says that, okay, drive and clean are closer to each other than drive and driver. Meaningfully, they are closer. Okay. So it knows about the semantic relationships. That's what we're trying to say. But again, this count-based stuff has some problems. What are the problems? It doesn't scale very well. I mean, if you have billion word data sets, it doesn't perform very well. And if you have small amount of data, the training is fast with the co-occurrences. Okay. And the advantages is very efficient. With the small data, it captures lots of information about it. And it is used for word similarity. Okay. And large counts are again problematic. With the word-to-vec approach, okay, it's very good in terms of scalability. You make your corpora as large as you want, it will work. Okay. But it needs lots of data to work, inefficient use of statistics. Okay. And it is generally used to be used for other tasks. You don't produce word-to-vec just to produce word-to-vec. Okay. And it can do complex patterns beyond word similarity. This is good, word similarity, similar words in terms of semantics and syntax, but word-to-vec can capture more information, just the word similarity. It will capture information such as analogy, and we are going to see a few examples of it. So the idea is going to be this. There is a technique called glove. Okay, this glove, like word-to-vec, is going to assign vectors to each word. Okay, and it is going to combine the idea of vector products of words, like the word-to-vec, but also it is going to do the counting. Okay, co-occurrences thing is going to do the same thing as we saw before. So it's going to combine both of them. Let's look at this idea. The idea is this. Okay, encoding meaning in vector differences, 2015 paper of Manning. Okay, Manning is one of the authors of the NLP book. Okay, let's look at this. Given eyes, what is the probability of seeing a solid in the same sentence? It is large, right? If there is a word ice in my sentence, what is the probability of seeing solid in the same sentence? Is large. Okay, if there is a steam in my sentence, what is the probability of seeing solid in that sentence? It's small. So they start taking these ratios on solid, okay, between ice and steam. So this division is large. How about this gas? Given ice, what is the probability of seeing a gas in the same sentence? It is small. But given steam, what is the probability of seeing gas? It is large. This over this is small. If both of them are large or both of them are small, then you're going to get around 1.0, around 1.0. So the crucial insight here is ratios of co-occurrence probabilities can encode meaning components. Okay, so if you do this kind of ratio comparisons, we could use this information to encode meaning of components, to encode vectors to the words. Okay, and again, this is co-occurrence probabilities. Co-occurrence probabilities. This is just an example, just the probabilities and etc. And before that, remember we did this to calculate the relationship between two word vectors. Just multiply them using the dot product. Now this is what we are going to do. Okay, this is just given j, what is the probability of I? But this one is just a ratio, and ratio is just using the logarithm of it. Okay, given a probability of x and given b probability of x, if you divide them together, that means that since we are doing the logarithm, this is log p minus log p again. Okay, but in that case, how do you say that? Okay, this is log p xa minus log p xb. Okay, so xa is wx wa minus wx wb. So I can do this wa minus wb. Okay, so it turns out that I am using these dot product stuff, and I can relate it to co-occurrences too. I am using both ideas at the same time. Co-occurrences and dot products. Co-occurrences will come from here. Okay, how many times did you see that there? Okay, and that will give me some ideas. Again, we are trying to combine the co-occurrence calculations with the word-to-vec ideas. If you do that, you need to take care of lots of balancing stuff. Some of the counts might be high, some of the counts might be low. Also, I need some stabilization. I am not going to go into the details, but if you assign, your word vectors using this idea, which is called glow, okay, your results will be better than word-to-vec results. And how we know that? First of all, since it is scalable now, like word-to-vec, I can train it on a very, very large data sets. Okay, and when you say, give me the nearest words to frog, okay, this is what you get. I know this one, frogs, syntax. Toad, I know this one. I have never heard of them. Oh, I know this one. Okay, so this is Litoria. This is Leptodactylidae. Leptodactylidae. I guess Rana. I don't know what these are. I know this one though, lizard. Okay, so again, this is fully unsupervised. It can recover, and it doesn't see any pictures, of course. This is NLP, right? And it can recover this kind of stuff. These are the closest stuff to frog. Remember last time, what did I say? Using this kind of things, you can pass the similarity questions of the TOEFL exam, right? Okay, this one includes lots of biological knowledge too, biology knowledge too, glow results. Okay, this is just visual results. How am I gonna make this more analytic, more number based? So what am I gonna do is the evaluation methods of word vectors. How am I gonna evaluate them? So there are two ways to evaluate them. One is intrinsic methods, the other one is extrinsic methods. Actually, we have seen examples of this before the word vects. Intrinsic means this: how good your vectors are by looking at some calculations on the vectors themselves. Okay, so I will evaluate my word vectors on intermediate subtasks. Okay, so these subtasks are not exactly end subtasks like useful NLP stuff, and you'll see why we say that. Extrinsic is a better way of verifying them. Okay, you use your word vectors in a real world NLP application, such as translation from English to Turkish, or such as classifying a tweet. Is a positive tweet, negative tweet, etc. Okay. So what are we gonna do? We are gonna do this. First, we are gonna look at this intrinsic stuff, intermediate subtask, which may not be useful for the real NLP task, and then we are gonna look at this extrinsic stuff. Intrinsic ones. The first intrinsic stuff is this. Okay. Give me the similar verse to frog. Okay, that's one. The other one is this. Calculate this value. We call this analogy. Given man and woman, okay, what is the corresponding word for king? Take the relationship between man and woman, apply the same relationship to this king. Okay, that's the formula. So how does the formula work? Subtract xa from xb, and add xc to it, and find such an xi that makes this calculation maximum. Okay, so basically find this arrow, okay, and take this arrow to, let me do this, okay, take this arrow and put this arrow on top of king, okay, and find the word that is closest here. Which word is the closest? And it should be queen, right? I should expect a queen here. So this is analogy, word vector analogy. Again, this is an intrinsic subtask. It is not useful as it is. And but if it works, it is something good. We know that at least for the analogies, we can achieve it. Okay, so this is one thing. And with the analogies, I see this. Okay, so these vectors are very similar to each other. Brother and sister, nephew and niece, uncle and aunt, man and woman, sir and madam, okay, king and queen, emperor and empress, etc. So these vectors are very similar vectors with the globe visualizations. But looking at these kind of visualizations, although it is fun and intuitive maybe, but we need numbers. How do you do the numbers? We have lots of data set. Okay, we ask the same question to people. If you ask me this one, I will say queen. Okay, and if you ask me this one, I will say madam. Okay, if you ask me this one, I will say aunt. Okay, so people form these kind of analogy pairs. Now I ask the same question to the globe words vector representations or word to vector representations, and I will try to get the same results out of them. Okay, and try to see how close I am. So that would be the number-based stuff. By the way, I can draw these kind of vectors in terms of the semantic relationship between them or syntactic relationship between them. See, these are all semantic relationships. Okay, sir and madam, king and queen, but these are syntactic relationships. Superlative, slow, slower, slowest, short, shorter, shortest. Good, better, best. Do I have good, better, best? No, I don't. Well, I didn't see it with the irregular words. Okay, so it captures syntactic relationships too. Okay, and if we put them in a number-based comparison, okay, so continuous bag of words and skipgrams are the ones that use word-to-vec approaches. Okay, so dim as dimensionality. So all of these examples, all of these techniques, they use 300 dimensional vectors. This is the size of the corpora that we have trained our system on. These are semantic relationships, syntactic relationships. This is kind of average between syntax and semantic. Okay, and the higher the number, better the system. As you see, Globe is performing better than the other systems. In one case, for the syntactic relationships, continuous bag of words is doing better, but Globe is very close. For the others, especially for the semantic relationships, okay, there is a large difference between continuous bag of words and the Globe. Okay, as you see, I cannot say that continuous bag of words is better than skipgrams or vice versa, but Globe is doing generally better than those. Okay, so this is one way to evaluate your word vectors, analogy examples. Okay, and they did some more experiments. They just wondered what kind of data set is, or what kind of data set size is good for these kind of calculations. Okay, for the Globe, it looks like larger the data set, better the results are. Okay, so with 1 billion tokens, semantic relationship is like that. 1 billion, 1.6 billion, 4.3, 6 billion, and 43 billion. It looks like these syntactic relationships are getting better and better. For the semantic ones, okay, the size does not matter that much, I guess. For some reason, I guess this data set is a little bit noisy. Maybe just because of that, the numbers went down. Okay, if I combine these two together, then I get this one. This is not better than that, but if I have a very large data set, this is much better than everybody else, both syntactic and semantic. How about the vector size? Vector sizes, it looks like 300 is the optimal point. Well, if I use 600, the numbers are a little bit better, but it is not worth using 2 times the vector size just to gain maybe 1 or 2% of performance. Okay. There is a 55 to 10% difference between these two, 100 dimensional and 300 dimensional. I say that okay, extra data, extra size is worth it, but here I cannot say the same thing. Okay, good. Any questions so far? So what we did was, it is another word representation technique called GLOW, and it is used widely to represent words. Okay, another one is this. Okay, similarity again. Human judgment. I will compare the human judgment with the word-to-vec similarities and the GLOW similarities. You ask people, okay, to give you a number between 0 to 10. Okay, 10 means that these two words are very similar. 0 means that they have nothing to do with each other. Humans say that the mean of humans. Tiger and cat are somewhat related, 7.35. Tiger and tiger, okay, it's the same thing. Book and paper are related. Plane and car are related. Stock and jaguar are not related much. Stock and phone are not related. Plane and car, okay. So these are the humans' judgments. And if I do the same experiment with word-to-vec or GLOW, this is what I get. Continuous bag of words, GLOW. Okay, so this part is on the 6 billion word corpora. Okay, 6 billion word corpora, and this part is 42 billion word corpora. And if you look at it, for the 6 billion, GLOW is doing good, almost all the cases, but Skipgram is good with this, with some of the numbers. What are those numbers? Human judgment.
Is it the data set?
But data set is here. Maybe the data set 6 billion. But different data sets, they don't have different amount of different data sets, they don't have same amount of numbers. Maybe they did not use the whole data set. Yeah, I don't know what the difference are. Wall Street Journal, it looks like that one. I think it might be the data set. But how come
the same model is present with different sizes, so I think they use some
part of the data set, yeah. Maybe. Yeah, it looks like GLOW is doing good in terms of human judgment too. Remember what GLOW does? GLOW says that, okay, I am going to use the occurrence counts, and I am going to use this ratio between two occurrence counts. So it is learning better in terms of, remember the advantage of co-occurrence matrices, statistical efficiency. So the GLOW is learning better in terms of statistical efficiency. It is making more of the data at hand. So that's why they say that for most of the data sets, it is doing better than the others. For some reason, they didn't run the others with the very large data set, 100 billion data set. Okay. So when you come to extrinsic data, extrinsic evaluation, remember the intrinsic evaluation uses this kind of, okay, human judgment similarity also the analogy, and etc. These are all applications that uses the word vectors only, and they are sub applications. They are not useful in the real world. But if I like to use these word representations for the real world applications, okay, we are going to use this named entity recognition. Named entity recognition. Named entity recognition is a NLP application that says in a given sentence, that says that, okay, this word is a person, this word is an organization, this word is a location, okay? So this is named entity recognition. And there will be an example of named entity recognition in my next slide set, and you're going to see it. For the real world application of named entity recognition, okay, it looks like for most of the data sets, okay, Glow is doing better than the other ones. Glow, word2vec, word2vec. These are standard applications of singular value decomposition on the co-occurrence matrices. Okay, so Glow is doing better than the others. What else? Word senses. Again, I think I looked at this problem a little bit. The idea of assigning a vector to a word is nice, but a word doesn't have a single meaning. Okay, a word has many meanings, so it makes sense to assign many words to different meanings of many word vectors to different meanings of words. For example, pike. Okay, pike has a sharp point or staff. It's called a pike. Okay, a type of elongated fish. There is a fish named pike. Okay, a railroad line or system. Sometimes you call your roads, okay, a pike, or sometimes a railroad is called pike. The feature, okay, sometimes it's called pike. A type of body position such as diving, etc. So 1, 2, 3, 4, 5, 6, 7, 8, 9 different meanings for pike. Yet if I use pike in a standard word2vec, I am going to assign a single word in it, right? And that will mess up my analogy calculations, and that will mess up my human similarity calculations. Okay, so I need to come up with a way of assigning different vectors for each meaning of pike. So how am I gonna do that? The idea is this. Okay, cluster word windows around words and retain with each word assigned to multiple different clusters. Okay, so you first treat each word occurrence as a different word and start assigning vectors to each different word. Then try to merge them together if their vectors are close. In that case, you are gonna get many different clusters for each word, and each one will have its own vector assignment. For example, let's look at that one. Okay, let's look at this one. Jaguar. The fourth meaning of jaguar is close to hunter, so I guess this is the animal jaguar. Okay, and this one is a jaguar. I think it is related to some musical instruments. Do you know what it is? Do you know what jaguar is in terms of musical instruments? Is there such a thing? Yeah, musical instrument jaguar is, Okay, the Fender Jaguar is an electric guitar by Fender Musical Instruments characterized. Okay, so it's kind of a guitar. I didn't know that. Did anybody knew that? Did anybody know that? Okay. Another one is Jaguar is a software package for Microsoft. What else? Another one is Jaguar is the car Jaguar, luxury and convertible Jaguar. So that was the first meaning. There are many meanings of Jaguar, and this system is figuring that out. And each one is assigned a different vector. And the vector for this Jaguar, the car Jaguar, and the animal Jaguar are so different. Okay, their vectors are so different, so far away from each other. So we achieve what we wanted. Okay, and some examples here. They say that, okay, tie, the word tie, how many meanings are there? It looks like it found 5 different clusters, and each cluster has these words in it. I guess the first cluster is the tie that you wear. Okay. How about the second tie? What is this? It's a tie game, right? 0-0 draw. Is that correct? Season, teams, winning, league, finished, championship. How about this one? Scoreline, equalizer, clinching, scoreless, replace. These are related to games too. How about this one? Wires. So this one is about wires and the cables. And this one is about musical stuff again. Some kind of a voice type. Soprano, baritone, and high, maybe. So it finds it. So assigning different vectors to different senses of a word is possible with word2vec or glow examples. Okay, it looks like I am out of time. Let me take a single question from you. After the question, I will take 10 minutes of break. Any questions? If you don't ask questions, I will go to the list again, and I will make you ask questions. Okay, I'm going to the list, okay?
Maybe I can ask a question.
Sure, okay.
So in Glow we stored in the vectors we represent as words the ratios between I think they're do we store all the ratios in the Glow vectors or?
Well, actually, no. But that's what we do. We calculate all those ratios, okay? Again, we do it in a smart way. If we try to calculate all the ratios between all the words, that's not going to be good. But we do some kind of a negative sampling. Okay, we sample the words, and those ratios will give us the probabilities of the similarity between the words.
So
while doing this, we do two things. We compare 3 things at the same time when we are doing these ratios. That's why statistically it is more efficient, we say.
So the way we represent words, how does it change? Isn't this?
It is exactly the same, just a word vector, 100-dimensional word vector.
Okay.
Okay, whatever I told you up to now, the word-to-vec or co-occurrence matrices or single value decomposition or the globe stuff, at the end they give you a bunch of vectors, a bunch of numbers for each word. Okay, 100 dimensional or 200 dimensional.
So their dimensions are always the same. So isn't but the co-occurrence for the co-occurrence matrix, the vectors means their co-occurrence, right?
No,
If
no,
I
no.
would-
Well, for the co-occurrence matrices, yeah, vectors are their co-occurrences, but since they are so large, they are 40,000 dimensional vectors, we use singular value decomposition to convert these to another space. In the other space, the numbers doesn't have to be the same type of numbers. It could be real values between 0 and 1.
Okay,
Sometimes
so
it is
it
negative,
will.
sometimes it is negative too. Also remember, we don't like words occurring so much, so frequently. Okay, we dampen them. So we have special functions to pre-process our counts before I do the singular value decomposition.
So the vector dimensions are the same, but the features in the vectors are different, right?
Yeah, vector dimension. See, this one, the example that I give you here. Yeah. For all the comparisons here, the glow or skipgram or continuous bag of words or the single value decomposition, small or large, doesn't matter. Their dimensions are all the same. They're all 300 dimensional vectors. Okay.
And
You don't expect
since
you don't expect them to be the same. In fact, if I run skipgram on the same data set 2 times, okay? If I run it 2 times, I get 2 different vector sets. I don't have to get the same vector set because I am using gradient descent, stochastic gradient descent. Okay? So, a word doesn't have a unique vector. The vectors can change from run to run. Important thing is, similar words syntactically or semantically should have similar vectors. Okay? Also, the analogy should work.
Okay, thank you.
Okay, good. Any other questions? Okay, let's take 10 minutes of break. Let's be here around 15:40. Eskiden. Tamam. Tamam oldu. Hadi görüşürüz. Okay, people. So okay, so let's try to use, what did we say before? We are not trying to find the vectors of words just because we like to find the vectors of words. We want to use them in real applications. Okay, we like to use them in real applications such as sentiment analysis or named entity recognition or translation or summarization, that kind of stuff, NLP stuff. So how are we going to do it? So we are going to, for example, do some classification. Let's review some machine learning stuff first. After that, we are going to find examples where we can use these vectors. Okay. Let me switch to some other slide set. Okay. So generally in machine learning, we have our data sets, and in our data sets, we have samples. What kind of samples? For example, this is our data set. Okay. This is our data set. Just, I am trying to make my pen work, but it didn't work. Okay. How about now? No. Okay, so this is my data set. In my data set, I have sentences like, let's say for the sentiment analysis task, again, I like Microsoft. Okay, so this is my sample number 1, and this is a positive sentiment. To Excel is great, again positive. For example, Windows is okay, plus just one sentiment. For Windows crashed again, this is a negative. Okay, so there are 5 classes for each sentence, and I like to assign each sentence to a class. So this is a sentiment analysis. It is very useful. It is a very useful application for the social media, micro blog analysis, etc. Okay, this is what we are going to do. Each one is a sample. Okay, each one is a sample, and each one is called, okay, a pair. This is my data and this is my class. Okay, for each xi there is a yi. These are xi's, these are yi's. I have total of, in this case, n is here 4. Okay, I have total of 4 samples along with their labels. Yi's are the labels. Okay, xi's are sentences. Xi are inputs, in other words, indices of vectors, sentences, documents, etc. Okay, yi are the labels. Okay, and we try to predict the classes, sentiment analysis or named entities or buy sell decisions, etc. Okay, and then later we are going to do more complicated inputs and label stuff. So they give us these kind of data sets, or we find them. We find these kind of data sets. No difference between them. And by learning from these xi, yi pairs, machine learning method, given this xi, okay, given a new xi, what is my new yi? I ask this question. If I get the correct answer, then I am doing good. If I don't get the correct answer, then I am not doing good. My method is not good. I need to do something about it, etc. That's the whole idea of machine learning in terms of natural language processing. Okay, I am not going to start very complicated machine learning stuff. We are going to start with our nice, okay, softmax approach. We are going to do this. We will get our inputs. Okay, we will get our inputs. Inputs are x. Given these inputs, what is the probability of this input has class 1 or 2 or 3 or 4 or 5? Okay, remember we have 5 classes. Okay, remember we have 5 classes. And for the sake of educational purposes, just to keep things simple, let's assume that our sentences are exactly 3 words like this. I like Microsoft, Excel is great, Windows is okay, Windows crashed again. Okay, I have 4 sentences, but each sentence contains only 3 words, no less, no more. Okay, why am I saying that I have 3 words only? Because I like to fix my input size. Let's say I am using skipgram word to vec vectors for each word. So this one is 200 dimensional vector, 200 dimensional vector, and 200 dimensional vector. My xi will be 600 dimensional vector. Okay, this sentence will be represented by 600 dimensional vector. Okay, very large vector indeed, yeah, but it's a vector of fixed size. And for this one, my label yi will be group number 5. This is group number 5, maybe this is 4, I guess this is 2, right? Okay, so my table is going to be 5, 4, 3, 2, 1. This is plus, 0, minus. There are 5 classes. Okay, so my input to my machine learning system will be the 600 dimensional vector for each sentence. Again, for regular sentences, sometimes they have a single word, sometimes they have 100 words. We are going to deal with it later. Okay, we are going to deal with it later. Question: maybe I could have done this. Okay, take the average of these vectors. I has a 200 dimensional vector, like has a 200 dimensional, and this one has a 200 dimensional. If I take the average of these 3 vectors, again I would have a 200 dimensional vector for the whole sentence, right? This would be nice. Why? Because doesn't matter if I have a single word sentence or 100 word sentence, the average of all the words would make a 200 dimensional vector, right? And I will solve this problem. So what is wrong with my approach? What is wrong with taking the average of all the words in a sentence and using that fixed vector to represent the sentence?
Different, same sentences with different, how can I say?
Word orderings.
Orderings will point to the same.
Yeah. Yeah. I like MS like I, okay. Ahmet likes MS and MS likes Ahmet would be exactly the same thing, right? So we like to keep the word ordering information. We like to keep the word ordering information. That's why I didn't take the average. But we are going to find nice ways of dealing with variable sized inputs later. So for now, let's assume we are doing this. So I am going to do this. Each input, okay, each input is a 600 dimensional vector and each output is a number from 1 to 5. Okay, each output is going to be 1 to 5. So how am I going to calculate? How am I going to calculate these P's? Okay, this is how am I going to calculate it in my machine learning approach. I will multiply, okay, I will multiply X with WY. WY are the weights of class Y, okay. Remember we have 5 classes. Let's say for class number 5, I have a W5 and its size is 600 again. There are 600 numbers for W5 and I multiply this input X with that 600 dimensional vector and take the exponential of it. And I divide this number with all the multiplications of all the class weights of X. And that's going to give me P given X probability of Y. Okay. So for each X, I am going to predict its probability and I am going to find the Y that has the largest probability. I am going to find the X, I'm going to find the Y that has the largest probability. Of course, in order for this to work, I need to find these W's, right? W1, W2, W3, W4, and W5. Okay, that's what I'm going to do. So this is a very classic machine learning example. It uses Softmax, okay, Softmax or Logistic regression. Okay, what is regression? Regression is this. Regression is a function regressor. Regressor is a function that takes some inputs and it produces a continuous real value. Okay, for example, this is a regression. It inputs this X value, right? It inputs this X value and Y value, and it produces a value between 0 and 1, this probability. This is a regression. They call this a logistic regression formula. Why? Because it produces values between 1 and 0. 0 means false, 1 means true. Of course, we expect any value between 0 and 1, so it's a regression between true and false. If the value produces 0.5, that means that my prediction is between true and false. Okay, good. So this is a classical machine learning example. If I have the right WYs and WCs, all of them, okay, this will work nicely. I will test this on any word. Let's make things a little bit simpler. Let's say that I have only two classes. Let's say I have only two classes. One of the classes are I have only two classes. One of the classes are, okay, plus class, Excel is great, Windows is okay, Windows crashed again, negative, 0 or 1, okay, 0 or 1. If I formulate my problem like that, this guy formula here is C is going to be just 2, okay, just two sets of W's, W1 and W2, that's it, okay, two sets of W's, and my results will be a binary result, either true or false, right, either plus or negative, true or false. And my final results could be visualized using this kind of a two-dimensional visualization. Let's say I used that, remember what was my input size, 600 dimensional word, right? I used singular value decomposition to drop from 600 dimensions to just 2 dimensions. So each sentence is represented by just 2 dimensions, just for the visualization. And in 2 dimensions, I put them on this 2-dimensional world. Okay, this is dimension 2. This is dimension 1. Okay, these green crosses or green dots are positive sentences, and these red crosses or dots are negative sentences. As you see, okay, I drew all of them. As you see, I like to divide this plane into 2. Okay, if I use a line like that, whatever remains under the line are negatives. Whatever is over the line are positives. These are positives. The rest are negatives. Okay, I am after such a line. This softmax is drawing that line actually. The task of this softmax actually, task of finding these weights, these numbers inside this WY and WC is actually trying to find a line that separates this space into 2. Of course, my space is not 2-dimensional. My space is 600 dimensional. But just for the visualization, I am assuming that it is just 2-dimensional. Since I am trying to find the 6-dimensional, 600-dimensional WY and W1 and W2, okay, I am making my search in 600-dimensional world. Okay, it's a very large world, and the result that I find is going to define a hyperplane. It's not a single line, but it's going to be a hyperplane. Okay, so this is what traditional machine learning does. Very, very simple approach. Surprisingly, it works very well for some cases. For some cases, it doesn't work. So that's the intuition of the classification. In this case, if you are using the logistic regression softmax, your parameter space will be r to the power c times d. D is the dimension of the vector, c is the number of classes. Okay. In the final case, what I did was I just dropped it down to the binary decision. In the binary decision, C is going to be 2. Okay, C is going to be 2. D is D. Whatever it is, I think it is 600. Okay, so good. Any questions so far? So I am giving you one way of using those I am giving you one way of using your vectors that you have obtained using either glow or word-to-vec or co-occurrences, doesn't matter. Okay. So the Softmax classifier is this. If you like, if you have more than 2 classes, 5 classes, if you like, of course, you can take them apart. Let's say you are interested in only one of the classes, like what I did, okay? Let's say if you are interested in one of the classes, well, in that case, take the white, y is this one, row of W, okay, and multiply that row with X, okay? W is one large matrix. Each row of W, okay, each row of W is responsible for class Y, okay? And I can do this calculation by multiplying Xi with Wy by summing this over. D is the number of elements in a vector, okay? And softmax is applied that way. Okay, good. So how do I train with the softmax? Training with softmax and cross entropy. This is important. Why is this important? Because softmax is good for calculating the probabilities of given inputs and already estimated W's. Okay. Now we are trying to find a way to calculate those W's. How am I going to do that? Okay. How am I going to do that? For each training example, remember our training example, like that one. Let me copy this. Okay, let me copy this. Control C and Control V here. Good, okay, it worked. I think it fits here. Remember our data set? For each sample, I have a label, and this one is a 600 dimensional vector, okay? For each training sample xi, yi, our objective is to maximize the probability of correct class y. We are trying to find those W's, okay? We are trying to find those W's. And if my W's, my weights, if I pick them right, those probabilities will give me correct class y. Okay, so this is equivalent to minimizing the negative log probability of the class. So what do you mean by given x, given this one, the first sentence, probability of having 1 or positive is the same as this one, okay, minus log likelihood of this one, okay, exponential of fy. What is fy? Fy is this one, okay? So multiply x, the vector of x, with the wy, and sum this over, and that's it. Okay, so let's look at this a little bit in a little bit more detailed way. Remember, I started looking at this log stuff or the minus log stuff when I started training. Without the training during the runtime, all I am calculating is this, okay? Apply this one and pick the y that maximizes this equation, softmax, okay? Pick the y that maximizes this one. This is runtime. During the training time, during the time where I am trying to learn this table, my data set, I am doing this minus log stuff. Why am I doing this? Let's look at this one. Okay. This is called cross entropy, loss error. Okay. So, concept of cross entropy is from information theory. It's just you're trying to see if something is similar to something. So it's cross entropy. Let's say, let the true probability distribution be P. P knows everything. Okay. P knows everything. And our computed model knows the probability Q. Okay. We like P and Q. We like P and Q to be very, very similar. I like their cross entropies to be close to zero. When the cross entropy is close to zero, then we are fine. We are doing good. Okay, that's why we are normalizing something. Okay, this is what we say. We say that for all the classes, given an input x, okay, multiply your model's result, take the logarithm of it, and multiply it with the real probability. Of course, with the real probabilities will be either 0 or 1. If the class is correct, it's going to be 1. If the class is not correct, it is 0. Okay, but in my case, since I am using the softmax stuff, it's going to be between 0 and 1. Okay, it's going to be between 0 and 1. Okay, so to calculate a value that tells me that I am doing good, this is a way of explaining it. This is called a cross entropy. Whenever the class is right, P is going to be 1. Otherwise, P is going to be 0. Okay, P is going to be 0. Assuming a ground truth probability distribution that is 1 at right place, at right class, and 0, then because of 1 hot P has to be 1 hot. 1, the others are 0. The only term left is the negative log probability of the true class. Okay. So in my case, what I am doing is, I will get the probability of the true class that I am assigning. I get the true class from P. I find my model's probability assignment. I take the log of it and I take a negative in front. This is called cross entropy, and this minus log comes from there. Okay, and in order to get these wy's and these wyj's, of course, yj is the member of wy. Okay, I need to minimize this loss function. Minus log of the softmax function. Okay, this one is good for deciding my prediction. Okay, this one is good for deciding my prediction. This one is good for training. Okay, minus log comes during the training only, not during the runtime, not during the testing time. Okay, not during the testing time. Okay, this fyi here is the same as this one. Okay, I take the power to f to the power. Again, the upper part is positive, the lower part is positive. The division is going to give you a number between 0 and 1. Good. Okay, now let's go back to our parameters. How many parameters do we have in the system? Okay, for each class I have y. For class yi, I have wyi, and this wyi is supposed to be multiplied with the input. Input size is 600 dimensional, so there should be 600 numbers in it, okay, for each class. And this one says that, okay, my whole parameter set is going to be 600 parameters for each class. And if I have just 5 classes, 600 times 5 is going to be my parameter set. So W is a 600 times 5, 3000 dimensional vector, if you like. Okay. And if I like to take the derivative of our loss function with respect to my parameters, is going to be a 600 dimensional derivative of the objective function. So in my 3000 dimensional derivative is going to be. So in my space there are 3000 parameters, and each parameter is going to be used in this equation, taking the derivative of the loss function. Okay, and after doing this, I will find my parameters, and my parameter is going to give me this decision boundary. Okay, it's going to be a neural network classifier actually, and that neural network classifier is going to divide my space into 2 parts. This black line is going to divide it. Whatever under this black line is going to be a one class. Whatever is above is going to be another class, 2 classes. Okay, Softmax, since it is everything, whatever Softmax is doing here, maybe this one is better, yeah. Whatever Softmax is doing, multiplying this input with the linear numbers, okay, is going to draw a line in this space. Is going to draw a line in this space. But what happens if I have cases like that? I mean, whatever you do, if you draw a single line, whatever you do, you are not going to successfully separate this space into 2 successfully. Some of the greens will be on the wrong side. Doesn't matter if I do this or do that or do that. As long as you draw a line, you cannot be 100% successful or 80% successful, because more than 20% of those the greens will stay on the other side of the line, right? That's not good. We don't like it. So here what I am trying to say is that this Softmax classifier, logistic regression classifier, cannot solve all of our problems. We need something more powerful. Okay, Softmax alone is not very powerful. It only gives linear decision boundaries. We need better than that. Okay, we need a decision boundary, maybe like this. I don't know how should I draw it, but it's going to be an exaggeration, but stay with me for a while. It's going to be an exaggeration. If my pen writes, I am going to show you my exaggeration. Okay. So I will do this. Okay, this is my decision boundary. Whatever remains above this line is going to be the reds, Okay. Whatever stays inside, I'm going to do it with the blues, okay, are going to be greens. So where am I going to find such a decision boundary? I mean, line was okay. It is simple. In 2 dimensions, line is just 2 numbers. In 3000 dimensional world, line hyperplane is just 3000 numbers, yeah. But how am I gonna find such a thing? Okay, to that we will use the neural networks. Okay, we are going to use the neural networks. In this case, our decision boundary is like that. Okay, decision boundary is like this. See, this blue line extends over the, goes around the plane and comes back. And it doesn't have to be continuous, it can be broken. Okay, and it will work. Note that this one that I drew and this one are doing exactly the same thing, but I mean the one that I draw here is very different than this one. So we can have different solutions to explain the same data. That's one thing that we can do with the machine learning world, and that's not something that we like actually. Okay, that means that our solution space is very, very, very large, and which one is going to be better than the others is going to be a tough problem. Okay, it's going to be a tough problem. Again, to solve this problem, we are going to use a gradient descent, and the gradient descent will be our solution. Whatever we do from now on, we are going to use gradient descent to find the parameters. But it looks like I am not going to have enough time to come to our next topic, neural networks, which is the basic foundation of the deep learning systems. But I think I will stop here. Maybe I should talk about this biological neurons and biological neural networks a little bit. On humans or many animals' brains, they have these cells, neural cells. Okay, these cells, of course, since they are cell, they should have a main cell structure. They should have a main cell structure, but these cells behave like each cell. Okay, I'm showing you 1, 2, 3, 4 cells here. Each cell is like a how should I say it? Each cell is like a softmax function. Okay, it has its own inputs. These are inputs, very, very large number of inputs. Okay, these are all inputs. It takes all these inputs and it does something on it, and then it produces output here. Okay, maybe I can connect the output of one cell to another cell, one cell to another cell, and continue this way. This is called a biological neural network. And there is physical evidence on our brains that our biological neural network works like this. The physical structure is like this, but how it works is similar to those softmax functions. Not exactly, there are differences we should see, but they are similar to each other. Next week, I think I will pick up from this position and I will continue, and I will connect this to NLP again, and we are going to see our first, second, third applications that use this kind of machine learning stuff. Okay, that's it for this week. Do you have any questions? Any questions? If there are no questions, then I will stop here and I will see you next week. Class is over.